Okay, so moving into our last unit on quadratics, we've now spent a lot of time in the last unit looking at both factored form and at standard form, how to move between them, and what kind of information you can find from both standard form and factored form, and how to get other key points such as the vertex, x-intercepts, y-intercept, and so on and so forth. We did touch on using vertex form a little bit in Unit 1. We're going to spend a lot more time on it now. So on the investigation that you would have done yesterday, you have taken a look at graphs of the form y equals a bracket x minus h all squared plus k, and you can see a few different values here. So for example here, you can see what happens as I change the a value. It affects how wide or how narrow the parabola is, and you can see if a gets into a negative value, the parabola starts opening down. Okay, which was the same kind of thing we saw when dealing with standard form as well. Okay, now more specifically, if you look at h and k, you see that right now the vertex of this parabola is 1, 1. Well, see what happens when I move h. The x value of the vertex moves along with it. Okay, whatever that h value is, it winds up matching up with the x value of the vertex. So it winds up being your axis symmetry. Okay, and you can even see that here as well. Okay, so if I wind up adding another expression here, and I just put in the line x equals h, you can see that, again, it gives you the axis symmetry. Okay, so that's what h value gives you. More specifically looking at k, you'll see as I change k, the y value of the vertex changes. Okay, so h and k together give you the vertex of the parabola, and again, this is called vertex form. So let's say you want to take a look at a few examples here. So here you've got the equation f of x equals negative 2 bracket x minus 4 all squared minus 7. Okay, you can take a look at it down here, and you see the a value is negative, it's negative 2, so we open down, and you can see the vertex is at 4, negative 7. Again, h is equal to 4, k is equal to negative 7. To see another example, we can look at 3 bracket x plus 5 all squared plus 1. Well, the vertex here is at negative 5, 1. Okay, again, k value is 1, h value is negative 5. It can be, and again, it's a little bit counterintuitive. You might see that the sign of the value for h is opposite what's in the brackets, because remember, the original form is already subtracted here. So if h is negative 5, you have x minus negative 5, which actually simplifies to x plus 5. So that's why the sign is opposite. But again, just keep that in mind as you're working with vertex form. Okay, so going back to the lesson here, so we now have 3 forms that we can look at. We've already looked at tons how to move between standard form and factored form. And getting vertex form is not too much harder once we have factored form. Once we have factored form, we know we get the x-intercepts. Okay, and once we have the x-intercepts or the zeros, we can average them out. This will give you the axis symmetry. Okay, once you have the axis symmetry, you can sub that into one of the original equations to find the optimal value, which gives you the vertex. Once you have the vertex, you can start making vertex form. Okay, so with that in mind, we now have 3 forms: standard form, factor form, vertex form. I want you to think about, either on your own or with a small group, which form it's easiest, quote unquote, to determine each of the different values. So which form is easiest to find the vertex from, the x-intercepts, the y-intercept, range, axis symmetry, and so on. So take a second, think about it, write down your answers, and push play and ready to go through them together. Okay, so let's go through these one at a time. I've wrote out for reference this basic standard form and vertex form in there. Factor form, you remember, just has a potential a value in front and 2 factors. Now, with the vertex, well, what form is easiest to get the vertex from? You're going to look at vertex form, because that h and k from vertex form is the vertex. Okay, so once you've got that part of the equation, or that key point in the parabola is known. So you want to get the vertex from vertex form. The x-intercepts are going to come from factored form. So just remember, for an example, let's say you had the equation y equals negative 2 bracket x plus 4 x minus 2. Okay, you could very quickly look at each bracket or each factor and solve for x once you have it equal to 0. So x plus 4 equals 0. Solve for x, you get x equals negative 4. Do something similar with the other bracket or factor, and you wind up with x equals 2. So x-intercepts are definitely easiest to get from factored form. Okay, with the y-intercept, well, that comes easiest from standard form, because remember at the y-intercept x is equal to 0. And if you put x equals 0 into standard form, well, what's going to happen? You have a times 0 squared, which is 0, plus b times 0, which is also 0, and all you're left with is plus c. So c is your y-intercept, so that's easiest to get from standard form. Okay, for the axis symmetry, a lot of people often think that factored form is the easiest one to get the axis symmetry from because you get your zeros or x-intercepts relatively easily. Then you can average them out to find the axis symmetry. And it's true, it's not actually that difficult to do. But even easier is to look at vertex forms. Remember, the axis symmetry is the x value of the vertex, so it's just the h value. Okay, so if you have the vertex, you already have the axis symmetry. So coming from there, you're going to get that much easier from vertex form. Okay, and last but not least, for the range, we talked about this a little bit back in Unit 1, that if you want to find the range of a quadratic, you really only need to know two things. Okay, so let's do a quick little sketch here of a quadratic. Okay, so let's just say I had a quadratic that had a vertex here and opened down. Okay, and then just for the sake of argument, let's say this vertex is at -3 and let's say 7. Okay, now I know the domain for this parabola is x an element of the real numbers. Okay, for the range, I'm looking for all the possible y values. Well, y does not exist anywhere above this vertex. It only exists below the vertex. Okay, so the only y values that are going to exist here are any y values that are less than or equal to the maximum value, which is 7. So in this case, y is going to be less than or equal to 7. So in order to get this, I need to know two things. I need to know where the vertex was, or at least where the optimal value was. Okay? And I need to know what direction it opened, because if it opened up, I'd have y is greater than or equal to 7. Since it opens down, its y is less than or equal to 7. So, well, which form gives me both the direction of opening and the optimal value? Well, it's going to be vertex form. I get the direction of opening from the a value, and the optimal value comes from the vertex, which is hk, or the optimal value itself is k. So vertex form is probably the easiest one to get the range from. Okay, so all of a sudden vertex form becomes very useful. It's the easiest way to get the vertex, axis symmetry, optimal value, and also the range. Okay, so with that in mind, let's keep working. So we're going to determine the equation, and we're given it's a transformation defined by a mapping rule. So we're told that the mapping rule from y equals x squared to our new quadratic is x plus 5, comma, negative 2y minus 7. And wants us to state the range of the transform function. Okay, so take it piece by piece here. It wants us to state the range, but in order to state the range, we have to know what our equation is so we can get some key information there. Okay, so let's think about this for a second, see what we can do. Okay, so first to remind us of how mapping rules work, let's take a look at my original graph, which is y equals x squared, because my new equation is a transformation of this one. So here's y equals x squared, and I've done some transformations to it, and it's going to create some new parabola. Now, one thing I want to point out here is that the vertex, again, on y equals x squared is at 0, 0. So using the mapping rule, remember what the mapping rule is for is to give me image points that correspond to original points on y equals x squared. So let's just say I'm taking the point 0, 0 and putting that in my mapping rule for x and y. Well, that means I'm replacing the x value with 0 and the y value with 0 as well. So it's going to give me, when I put it through my mapping rule, 0 plus 5 and negative 2 times 0 minus 7. Okay, so again, do each coordinate separately. 0 plus 5 is 5. Negative 2 times 0 is 0, minus 7 is minus 7. So my vertex of my new parabola is going to be at 5, negative 7. Okay, the original vertex was at 0, 0. I went through this transformation, and I wound up at 5, negative 7. Okay, the other way you could think about this is trying to get the transformations from here. My x values, I have a translation to the right, to the right 5. Okay, I have a shift that's down 7 for the y. And this negative 2 does two things. Okay, it does a vertical stretch of factor 2 and a reflection in the x-axis. Okay, and these are all the transformations that we looked at back in Unit 1. Okay, so once I have the vertex, I can actually start creating vertex form. So remember, vertex form is y equals a times bracket x minus h all squared plus k. Okay, and again, I know my vertex, so that gives me both my h and my k value. So I have x minus 5 all squared minus 7. Okay, so the only thing I'm really missing in this equation is my a value. Okay, and I know we're used to solving for a values by subbing in points for x and y and solving for a, and if we had points, we could certainly do that. If we wanted to, we could find more points using the mapping rule, but remember here that this value right here, this -2, that gives me my vertical stretch factor and my reflection, is my a value. Okay, and we saw that when we did mapping rules back in the first unit. So in this case, a is equal to -2. Okay, and that comes directly from our mapping rule. So my equation is y equals -2, bracket x minus 5 minus 7. Okay, so that's the equation of our transform quadratic, which means we're almost there, but now we have to find the range of this transform function. So to get the range, I always recommend, when you're trying to do domain and range, do a quick little sketch to give you an idea what the picture looks like. Okay, it makes it a lot easier than trying to visualize what's going on in our heads and just taking a guess. So I know just from this quadratic, I want to make a very accurate sketch here. Now I did miss my squared here, sorry about that. I know my vertex is at 5, -7, so I'm going to put that somewhere in the right quadrant. So 5 in the x, -7 in the y is somewhere down here. Okay, and I know that my parabola opens down because my a value is negative. So what I'm trying to draw here is a parabola that opens down that has 5, -7 as a vertex. And just a quick rough little sketch. It's going to look something like this. Okay, now, and this is all I need again to find out the range, because I know that the only y values that exist in this graph are the ones that are below my maximum value. So my range here is going to be any y value that is smaller than or less than or equal to -7. Okay, we can just check our answers up here. There's our equation, and there's our range. Okay, so anytime you want to find the range of a quadratic, you want to be in vertex form, because it gives you the vertex, you have the direction of opening, make a quick little sketch, you can get an idea of the range from there. Okay, so let's keep going, let's take a look at another one. Okay, so a reminder here that again, the general vertex form for a given vertex hk is f of x equals a bracket x minus h all squared plus k. So h and k is known, hopefully you'll know the vertex, and a is going to be unique to each parabola in the group that have the same vertex. So all this means, for example, if you take a look at this example, you want to find the equation, and it says in standard form, we'll deal with that later, but the equation of the quadratic with vertex of -3, 5 passing through the point -7, 4. So for starters, knowing that I know that the vertex is -3, 5, okay, I can go look at Desmos here, and here's a parabola with a vertex at -3, 5, but I can create so many different parabolas that have that vertex. Okay, they all are going to have different, some of them are going to be narrower, some of them are going to be wider, some will be opening up, some will be opening down. There's infinitely many parabolas that will have this vertex. Specifically, I'm looking for the one that passes through the point -7, 4. So I need to find an a value that makes this parabola pass through the point -7, 4. So -7, 4 would be somewhere up here, so I'd have to play around with it in order to get it to work. Okay, so I might be able to approximate it here, but again, I'm looking for an exact value. So I need to find the a value that makes this parabola pass through that given point of -7, 4. Okay, so in order to do that, I'm going to start with my vertex form. Okay, and since I know what the vertex is, I'm going to sub in those values for h and for k. So that's going to give me f of x equals a, x, so x minus -3 is x plus 3. Okay, don't forget your squared, and then plus k, k is 5. Okay, so again, what I'm looking to solve for here is a. Okay, and just like what we were trying to do when we were solving, trying to find equations in factored form, we have to solve for that a value. So remember, if I'm looking to solve for an a value here, I have 3 unknowns right now. I have an x value, which is a variable, y or f of x, another variable, and this a. So if I want to solve for a, I need to have values for x and y. Where do I get values for x and y? They come from a point. So I know this parabola has to pass through -7, 4, so I can sub that point in for x and y and solve for a. Okay, we'll continue this in part 2 of the video. We'll see you over there.